So today we have an interesting geometrical problem. The diagram is on the screen with all the given details, but there are few things in this diagram that you have to note while solving the problem. The first thing is that, as you can see, these three line segments are meeting at a particular point B. So this point is also the point of contact for this yellow tangent line, okay? And the second thing over here is that the blue line segment that you can see is not passing through the center of the circle. Now by using all these given details, the question over here is to get the length of the blue line segment, that is the line segment AC. So this is Anmol, and now let us see the solution. How can we solve this problem? Okay, now let us start with the solution. So the first thing that I will do is I will utilize the fact that this particular yellow line segment is tangent to the circle. So we know this particular thing, that if there's a circle and we draw a tangent line to this circle, the angle formed at the point of contact between the tangent line and the radius will always be 90 degrees. So the same thing we will utilize in this diagram. So we already have the circle, we also have the tangent line, and now to draw the radius I have to mark the center of the circle. So recall that it was given that the center of the circle does not lie on this particular blue line segment, and by seeing this diagram we can say that yes, the center will lie below this line segment. So let the point of center be over here and let it be point O, okay? So now I will draw a radius, that is a line segment joining the points B to O, okay? The angle formed at the point of contact between the tangent line and the radius will always be 90 degrees. Hence this particular angle is 90 degrees, and that is angle ABO, and it is having a value 90 degrees, okay? Now I will draw one more radius in this particular diagram, that is a line segment joining the points O to C, okay? It is also a radius. Therefore, the length OB and the length OC are equal because they are the radius of the same circle. Now recall this particular theorem related to the circle, that is, in a circle, the angle subtended by the chord at the center is double the angle subtended by the same chord in the same segment. For example, if we take this one as the common chord and assume that it subtends an angle theta at the circumference, therefore it will subtend an angle 2 times theta at the center of the circle. So let us utilize the same theorem over here. The common chord that we will take is the chord BC. So I am taking BC as my common chord. Therefore we can see that the angle BPC is one of the angles subtended by this chord at the circumference. Why I am telling one of the angles? Because this chord can also subtend an angle like this way at the circumference, okay? There are infinite many possibilities. Out of that, this one is already present in this diagram. So I will label this one as alpha. So I am taking the angle BPC as a variable alpha. Now according to the theorem that we just saw, the angle subtended by this chord at the center will have a value 2 times greater than the angle subtended by the same chord in the same segment at the circumference. So we have already assumed that the angle subtended by this chord at the circumference is having a value alpha. Therefore the angle subtended by this chord at the center would have a value 2 times alpha, okay? Now look in the same particular triangle, we can see that we have already got the value of the top angle as 2 times alpha, and as this particular triangle is an isosceles triangle, the value of 2 of the bases would simply be 180 degrees minus 2 times alpha divided by 2. So this thing will ultimately simplify and give me 90 minus alpha, okay? This is the value of this both angle. Keep this equation as it is, so let me write it. Now we can see that in this particular diagram we have marked most of the angles except this one. So what I will do is I will simply mark this one as another variable, let it be equals to theta. So over here this angle be theta, that is I have taken the angle BAP as a variable theta, okay? This I have just assumed, or we can say I have let, assume is not a correct word, I have let it this particular angles as variable, okay? Now we can see that here we have a triangle and this line is a straight line. Therefore we can use the exterior angle property, that is, if there is a triangle and it has a straight line in the base, the value of this particular angle, that is K, would be equals to addition of the two inner angles, that is A plus B would be equals to K. This is the exterior angle property. So by using the same property over here, we can get the value of the other interior angle, that is this particular one, and it would be equals to alpha minus theta, okay? So what we have just got is the value of the angle ABP, and that is equals to alpha minus theta, okay? Now look carefully in this particular diagram. We can see that the complete angle OBA is equals to 90 degrees. The value of the angle PBA we have just got as alpha minus theta. Therefore the value of the remaining angle, that is the angle PBQ BO would be equals to bigger angle minus the smaller angle, that is going to be 90 minus alpha minus theta, and this thing will simplify and give me 90 minus alpha plus theta. So this is the value of the angle PBO, that is this particular angle. Now we can see that the value of the angle PBO we have just got over here. The value of the angle OBC we have previously got, and it was 90 minus alpha. So it's a simple algebra that the value of the complete angle PBC can be written as the addition of two angles, that is the angle PBO plus the angle OBC. Now the value of the angle PBO we have just got, and it is 90 minus alpha plus theta, and the value of the angle OBC we have previously got, and it is 90 minus alpha. So plus 90 minus alpha, so this thing will simplify and give me 180 degrees minus 2 times alpha plus theta, and this is the value of the angle PBC, that is the complete angle over there. So now keep in mind we have got the value of the angle PBC, and I'm just removing some of the markings in this diagram, that is the radius of this circle, this angle 2 times alpha, and all this 90 degrees and all this. And by utilizing all these things that we have just erased, what we have got is the value of the angle PBC, and that is 180 degrees minus 2 times alpha plus theta. Now look carefully in this particular triangle. One of the angle is 180 degrees minus 2 times alpha plus theta. The other angle is alpha. Therefore, by angle sum property, the value of this third angle would simply be 180 degrees minus this minus this. And by simplifying this equation, the value of this angle will turn out to be alpha minus theta. Okay. Now I'm just removing this thing also from here, because we have to now just concentrate between two triangles, and that is the triangle ABP. So let me write it over here. The first triangle that we are taking is the triangle ABP. In this particular triangle, the value of angle A is equals to theta, and the value of the angle B is alpha minus theta. Now the second triangle that we are going to take with it is the triangle ABC, that is the complete triangle. So now instead of labeling this triangle as ABC, I will just label this thing as ACB. So in this triangle we can see that the value of angle A is theta, and the value of the angle C is alpha minus theta. So we can see that in the triangle ABP and the triangle ACB, two of the angles are equal. Hence, these two triangles are similar to each other because of the property angle-angle. If two angles between the triangle have the same value, they are similar to each other. Now as these triangles are similar to each other, and we have already labeled this thing according to the correspondence, therefore the ratio of their sides would now be equal, that is AB upon AC would be equals to BP upon CB, and this thing would be equals to AP upon AB. Now I'm just removing this thing from here because these line segments are having a nice values according to this diagram, so we are going to put that value over here. So now according to this diagram, we can see that the value of the line segment AB is 3 units. The value of the line segment AC is the thing that we have to find, equals to BP upon CB. The length of BP is this green line segment that is having a length 2 divided by CB, that is ultimately this red line segment having a length 4, and this thing is equals to AP upon AB. Yes, we can compare these two ratios in order to get the value of AP, but that is not asked in the question. The question is to find the length of this blue line segment, that is AC, and in order to get that one, I will compare these two ratios. Therefore, 3 upon AC equals to 2 upon 4. 2 upon 4 can be written as simply 1 upon 2. So 3 upon AC equals to 1 upon 2. Simplifying these two ratios, we will get the value of AC, that is going to be 2 into 3, 6 units, and this is the answer that we were looking for. So this was my way to solve this particular problem. If you have any other method other than this, or else if you have any other question that you think I should try, you can do comment below, and if it's hard to comment, you can email me, or else you can send it to me on my Instagram. The link is in the description.